Hello, ladies and gentlemen, and thank you for standing by. Welcome to this ASM webinar on digital image correlation in support of complex testing of advanced materials. I'm Joanne Miller, Senior Editor with ASM International, and we're glad you could join us. Today's presentation is part of the ASM webinar series designed to provide information that you can apply to improve quality, efficiency, and performance. This webinar series supports the needs of our members, customers, and the materials community at large. This series also supports the outreach needs of the leading corporate supporters of ASM and its affiliate societies. The sponsor of today's webinar is Zwick Roel. Zwick Roel is one of the world's leading suppliers of material and component testing systems. The company supplies both standard and tailor-made solutions for the most demanding requirements in R&D production and quality assurance across more than 20 industry sectors. Privately held, the company's consistent focus on innovation and commitment to outstanding quality have supported its growth in markets worldwide. Additional information about Zwick Roel may be found on their website, zwickroel.com. We're proud to have Zwick Roel on board for today's webinar. Before we begin, let me mention a few housekeeping issues. If you're having technical difficulties in joining the GoToWebinar session, dial 877-582-7011. All participants will be in a listen-only mode during the presentation. Feel free to submit written questions at any time using the Q&A window located in your upper right corner of your screen. Click the question mark button to open the Q&A window, type your question in the box, and click the send button. We'll answer as many questions as we can at the end of the webinar. We're proud to host today's webinar. For over 100 years, ASM International has served the materials community by providing scientific, engineering, and technical information, as well as education, networking, and professional development. Advanced Materials and Processes is ASM's flagship technical magazine. It provides information about leading-edge developments and trends in engineering materials and the methods used to select, process, fabricate, test, and characterize them. The magazine also covers emerging technologies such as nanotechnology and additive manufacturing, in addition to management topics of interest to scientists and engineers. Visit us at the website found on your screen. With that, I'd like to introduce the instructor of today's webinar, FADI Abu Farha. FADI is currently operating a startup, FADI AMT LLC, focused on the advanced characterization of a wide range of materials with the aid of optical metrology, particularly using digital image correlation, or DIC. FADI received his PhD in mechanical engineering from the University of Kentucky in 2007. After that, FADI was an assistant associate professor of mechanical automotive engineering at Penn State University and Clemson University's International Center for Automotive Research. FADI's primary area of research was lightweight materials and their manufacturing. He received several Best Poster and Paper Awards at multiple events, including NAMRI SME and TMS, and won the Young Researcher Fellowship at the 3rd MIT Conference on Computational Fluid and Solid Mechanics. FADI is a recipient of the NSF Career Award, the SME Young Manufacturing Engineering Award, the SAE Ralph Teeter Award, and the TMS Light Metals Division Award. It is a pleasure for me to introduce FADI.
Thank you, Joanne. Good afternoon, everyone. This is FADI, and I will be presenting today's ASM webinar. But before I start, I would like to thank ASM very much indeed for this opportunity to let us present about this important topic. And we hope you all find it interesting and useful. I will start with a very, very short bio sketch. Of course, Joanne kindly presented or gave an overview of my history, but I wanted to start with a quick snapshot of my work in academia. And without repeating the bio sketch, I wanted to focus on just a couple of items here, which is in the past 15 years, I worked on different aspects of lightweight materials and their manufacturing. And my focus was on modeling or material modeling, experimentation, and finite element simulations. So with that experience, the next chapter of my work has been technically focused on experimentation, and the shift has been on high quality experimentation in order to support other people in the field in their work on modeling and finite element simulations and research and development. With that, we just wanted to provide a quick snapshot of the two organizations I represent and I work with. Of course, Zwickol, as presented by Joanne, has been building materials and component testing systems for over 160 years. And we at AMT focus on advanced material and component testing with focus on optical measurement techniques, including digital image correlation. And between the two of us, we've been working with many industries, but at least in the automotive sector, we've worked with several organizations or several OEMs and suppliers, both on the system development for their internal testing, as well as in supporting these OEMs and suppliers with their material testing needs, and again with focus on the latest advances in material testing systems and also technologies for strain measurements. So back to the webinar today, we will talk about digital image correlation and how it is used in support of complex testing of advanced materials. And to start, of course, we need to introduce the IC and define it. And in this slide, I have a very simple schematic of what the IC represents. And on the top left, we can see that we have usually one or two cameras, or sometimes more. The typical configuration has two cameras, and that's what we call 3D DIC. And the two cameras are usually configured so that they look at the object somewhat perpendicular to the object as the object is moving or deforming. Each camera takes basically an image of the object as it's deforming, and those images, in this particular case, we have left and right, those two images are correlated together with an algorithm to define the exact location of every sort of point in the image. And to define this particular point, we have a certain number of pixels in every image. And one particular example is shown at the bottom left. This particular image has many pixels, and to provide a basis for the correlation, instead of tracking each particular pixel, we group pixels together in a particular group that we call subset. And that subset is basically defined in each one of the images on the left and the right. And by writing an algorithm that tracks these subsets during the test or during deformation, we can basically define the 3D coordinates of each one of those subsets in 3D space during testing. When we correlate these together and we track the displacement of each subset, now we have the displacement information for each subset, and that translates into deformation of the material sample as the test is basically is undertaking. So an example of this in real life is shown on the right hand side. This is a typical tension testing machine with a tension sample, and you can see the DIC system, which is obviously here a 3D configuration with two cameras. And the test would be running and the material would be deforming just like any typical tension test. And as you can see in the video that is playing right now, you could see the sample stretching, and as the sample stretches, we accumulate more strains, and that is done again by the digital image correlation algorithm that we said or we talked about, where we track the deformation of the sample at different locations. And that particular video that you see here is a typical example of any DIC test. We see colorful map we call it a strain map, which is an overlay over the entire sample as it's deforming. And this colorful map represents the amount of strain or the intensity of strain, just like a typical finite element simulation, up until the moment of fracture. So now that we define the IC, where do we see the IC, and what is the importance of the IC? What is the critical need for the IC? In essence, we see the IC in many tests, but the vast majority of it is still the simple and humble tension test, just like the test that you see on the screen right now. So in tension testing, when we use the IC, we get again one of those videos that I showed earlier, and we can construct a stress strain curve that looks like the one that is building up right now on the screen, and ultimately we characterize the deformation of the material. The critical point here is that we can absolutely construct the same stress strain curve without the IC. You can do the same thing with the same level of accuracy with a conventional extensometer. And we have to remind everyone here that digital image correlation is nothing but a strain or a deformation measurement technique. That means that your stresses, which come from forces, have nothing to do with the IC. So on a stress strain curve, the vertical axis is generated by a load cell. The x-axis generated by an extensometer, or in this case, the IC. So the IC only affects the x-axis of your measurement, and it doesn't affect the vertical axis. And so in a case like this, if we can generate the same exact thing with an extensometer, why do we need the IC in the first place? Before I explain why, I wanted to indicate that sometimes people think of the IC as just a fancy extensometer. This is the latest technology in strain measurements, and so sometimes people think that it's good to have the IC just because it's the latest technology. And that is technically not correct, because there are multiple types of extensometers. They work in different fashions, and they basically follow different technologies. Some of them are mechanical clip-on extensometers, but some of them are actually more advanced digital. And then we still have laser and video extensometers, and even some of the latest generations are still labeled as optical extensometers. So we have a wide variety of contact and non-contact extensometers. Some of these are actually multi-axial, which means they offer multiple capabilities. And that's where we need to be careful about how do we compare the IC to these extensometers. When is the IC better, and when is it just basically as good as those? And when do you have to consider the IC, and when are the cases where you technically can achieve the same objective without the IC? So that's what we are going to try to cover today. We will start with a simple fact. The fact is, the majority of material testing practices that happen every day in all of these labs, whether it's academic or industrial, the majority of them can be done without the IC, period. And they can be basically done with other forms of extensometry. In many cases, extensometry is easier, faster, and cheaper. And in many cases, extensometry can do what the IC cannot do. And that means, of course, that the IC sometimes is not the best solution for you, and some of those extensometers can do a better job. So what is this webinar about then? Well, we are still going to try to give all aspects, whether it's positive or negative of both, but in today's webinar, we are going to try to focus on those particular application cases where you certainly need the IC, and the IC provides a value, in some cases very important and critical value, that cannot be matched by extensometers. And we want to distinguish between them so that you can make the right choice for the use of the right technology for your application. And for this particular webinar, I say that we have about 5 to 10% of testing cases where DIC basically has a position. And I break it like this: about 5% of those testing scenarios simply cannot be done without the IC. And hopefully today we'll show you examples of those cases where it's really difficult, if not impossible, to get the same type of data without using the IC. The other 5% can be done by both technologies, digital image correlation and other extensometers. However, using DIC gives you that advantage. So overall, the way I picture it in my daily testing life is that we have a spectrum of testing applications and cases. In about 5 to 10%, DIC is invaluable. For the rest of it, can you use DIC? Absolutely. Can you use it for the entire spectrum? I believe not. And so there is a certain position for it where it's really critical, and we want to focus on that critical position, and that's the 10% that I want to cover today. So today's webinar, we will talk about the uniqueness of DIC and highlight the particular areas in material testing where you can really use DIC to transform how you characterize materials and how you understand their deformation and failure. And to do that sort of effectively, we will do it primarily with pictures and videos. We will minimize the text and we'll just focus on examples from real life testing scenarios in which we highlight the value of DIC. And also during that, we will also indicate comparisons with conventional extensometry. To keep things in perspective, because we've done several seminars or webinars like this before, and we tend to go, we can spread really wide in terms of the number or types of tests that we can cover. But to stay in focus today, we will cover only two types of tests, the tension testing and the biaxial testing, for two simple reasons. The first one, which is the tension test, this is the most popular test out there, as we mentioned earlier. And we want to show that even for this simple, not very sophisticated test, or at least that's how it's typically viewed, you will find certain areas where DIC brings a lot of value. And we think, with the diverse audience that we have today, that we can connect with most of you, because at least everyone who's done material testing has been exposed to some form of tension testing. And so there should be here a nice relationship to the things that you are doing in your lab right now. The biaxial testing is just slightly more complicated than the tension test. Maybe it's not as popular, but it provides us another platform for comparison. So it's a step up from tension testing. And here we show examples again of the uniqueness before we go, hopefully in future webinars, to the other complex cases like shear, bending, compression, and also a dedicated webinar on component testing, where we have, of course, a totally different perspective on how we can use these technologies to help us in component testing. And to stay true to the title of the presentation, we will focus our examples on the use of advanced materials in the automotive sector. This is an important sector, and we see a lot of use of materials that really didn't exist 5, 10, 15 years ago. So there's lots of materials that are new to the sector, or sort of improved to the level that requires a change in the material testing system or approach. This includes advanced high-strength steels and aluminum alloys for lightweighting, as well as some foils that are used in car batteries. So let's start with the tension testing. And typically tension testing is done for the purpose of obtaining the mechanical properties of the material and also evaluating the deformation homogeneity of it. On the right-hand side is a typical tension setup, tension machine with a test sample up to failure. So a standard tension test per any standard, especially the ISO 6892, one of the most popular or equivalent ones from ASTM or GIS or DIN, are the most commonly performed types of tests out there. Naturally, in these tests, we use conventional extensometry. In fact, most of these standards are written using conventional extensometry, in particular clip-on extensometers or contact extensometers. And they are actually adequate. Of course, if they were not adequate, they would not be covered by the standard, but usually the standards describe exactly how you could use these conventional extensometry techniques, basically to get your measurements correctly and accurately and reliably. In terms of the standard itself, one of the aspects of the standard is basically the sample geometry. And I wanted to highlight this particular aspect of the test to drive how we can go from conventional extensometry to special extensometry and, of course, DIC. and that is the sample geometry. So if we are to talk about typical testing, we should always adhere to the standard sample size that is dictated by ASTM or ISO. However, there are so many cases where we have and sometimes must deviate from these standards. And in here, in this slide, I actually just listed a few cases where we have to go smaller and a few cases where we have to go larger. And some of the cases where we have to go smaller from the ideal standard size is when we have a limited supply of material, especially in material development practices by most of the steel and aluminum industries. Sometimes there is a limited amount of material, so you have to make this sample smaller, subsized, or miniature. And or when you extract samples from components and you don't really have the luxury of extracting a standard size sample. Also, when we go to particular conditions of testing, like testing at high strain rates, you have to go with smaller samples. And then we go to special cases, like you have an interest in a particular zone, such as a weld line. Then you have to go even smaller than what we call subsized, and we enter into the miniature samples. On the other side, if we go to other scenarios, like when we have thick materials, in order to maintain a good aspect ratio, you are forced to use larger samples in order to maintain a good length to width aspect ratio. Another special case is finite element simulations and fracture modeling. For those particular users of finite element and who require special fracture models to run their simulations, as we will explain later, you will need larger samples in order to satisfy meshing requirements in your finite element basically mesh. And last example here is when we want to study the deformation homogeneity of the material, especially in steel coils or aluminum coils, we tend to go to supersized samples or extra oversized samples, and we will show examples for each one of those categories. And we will show how in many of these cases that are listed here and some others, DIC has to be brought in simply because of the limitations with existing extensometry. And we start with a simple case. This is a standard tension test on a steel sample. Stress strain curve is being developed, and you can see the material is deforming quite nicely, and the stress strain curve looks like a typical steel or aluminum stress strain curve under normal conditions. And of course, obviously, this test can be done by a typical extensometer. No difference, you will get the same stress strain curve. The only advantage here that DIC brings in is the ability to visualize how the material is deforming and where is it failing exactly. And that could be sometimes informative depending on the type of material that we're testing. But let's go to those cases where we have to go smaller and larger. This is a subsized sample. This is from a material development effort for a steel grade. And with the limited material supply, we had to go with smaller samples. But more importantly here, this was a special development material, and we wanted to study the exact behavior of the material. And that's where the IC offers something that cannot be offered by conventional extensometry, which is how the material is deforming. Is it uniform? Is it not uniform? And in this particular case, you can obviously see that the material is having a banding response that is important to identify, which cannot be identified without DIC. Another case here is a miniature sample. This is taken from a cast component, and of course, with the limited location that you can take the sample from, obviously the sample size has to drop. And now the question comes in, can I do this with extensometry? Technically, you should be able to if you have flexibility with the extensometer. Of course, you cannot use clip-on extensometers that easily here, but some of the video and non-contact extensometers can be adjusted to track a smaller length. In this case, it's a 12 millimeter sample, so you could potentially do it. However, again, the limitation stays there, which is the ability to see how the material is deforming and how is it failing under these loading conditions. Now we go to another extreme. This is an example of an extremity in the sample size where we have to go to the miniature sample size. And this is a weld line, basically. A sample was extracted along the weld line. This is a laser welded aluminum sort of component. And we extracted the sample along the weld line. It was about 0.7 millimeters wide and about 8 millimeters long. This is where, again, could you use conventional or non-contact extensometry? Potentially, yes, I would say very difficult. And so that's where the IC offers a significant advantage in terms of identifying the true behavior of the weld material and also how does it deform. Just one note here, this stress strain curve is coarse not because of a load measurement issue, it's simply because the material is a 5000 series aluminum, which obviously will bend under tensile loading. So now let's go to the next or the other side of the spectrum, which is larger sizes. When do we need to do this kind of testing with samples that are larger than standard? This is a technically still a standard sample. It's a 20 millimeter sample. It's a European standard versus the North American one. So it's larger, about 20 millimeters wide, about 100 plus millimeters long. And this can be definitely done with conventional extensometry. When we go a little bit larger, to 30 or higher sort of widths for particular purposes. One of those is fracture strains, identification of fracture strains in order to support finite element simulations. You can see in this video how the strains were not only captured, and I'm going to repeat this video. Notice how the strains were measured exactly at the point where the sample fractured. And that's very important. You can see 1, 2, 3, 4, and 6 millimeter long extensometers. With a conventional extensometry, you can only do like nominal strains. In this case, we need the nominal strains as well as the local strains, and that's what define the fracture strains of the material. And that cannot be done without the IC. And that's a particular example where you need the IC in order to satisfy this particular requirement. And in some cases, you have to go even wider and longer because so many cases require larger mesh sizes for finite element. So this is one of the larger samples, not necessarily the largest, but the larger samples that are used for the same exact purpose. And you can see here again, there are multiple small virtual extensometers applied to the point of fracture in order to obtain the fracture strains for this 40 millimeter wide sample, which will allow the user to match their mesh size in a finite element basically setup to around I would say 6 millimeters. You could go potentially to 8 millimeters with this kind of a setup. Last example on the first type of tension tests I'm covering today is basically testing extremely large samples. And this is something done in characterizing an entire coil. In this particular case, this sample was about 750 millimeters long, and it was taken across an entire coil. And the idea was to try to test the sample, not necessarily to failure, but rather to test it to a particular point in order to evaluate the uniformity and homogeneity of the material. And you can see this very clearly in the bottom left corner of this video. You can see how the strains are not uniform at all in this particular coil, and it was a development coil, and that was the intention of a test like this, which is to show whether the coil is homogeneous or not. And that can be done with the IC, cannot be done with conventional extensometry, because not only that we want to cover a very large area, but also we want to cover the entire spectrum of strains along the entire sample, and that is the section view that you can see there. So up to here, we've talked about seemingly standard or conventional tension tests, and we've highlighted many cases where typical extensometry cannot be used. Now we go to another set of tension tests, but they're technically more complex in nature, that will also invite applications for the IC to complement or replace conventional extensometry. And so I have picked here a couple of cases. Adhesive joints or testing of adhesive joints. This is a standard test in essence, but we will show how the IC can improve it. Cyclic tension compression testing. This is a very custom test for spring back prediction. And we show how the need for side monitoring with the IC brings a significant value. Then we will just provide a very quick snapshot of high rate testing or testing at very high strain rates. And again, this is a very special area where the nature of the test, the high speed and other challenges makes it really difficult to do this kind of testing without the IC. And finally, I'm going to just touch on a couple of examples of foil testing, foils that are thin or extremely thin, and how DIC can sort of allow you to obtain the strains in a correct manner so that you can construct a meaningful stress strain curve. So let's start with the simple case of adhesive bonded joints. This is a standard test. And typically, you basically pull this on a standard tension machine and you report the load displacement. This particular case, we use the DIC in a special case, in a side monitoring mode, and you can see how we are able to monitor that very thin layer of adhesive during the test, which is at the interface between the two sheet metals. And in this case, we show how the DIC is able to define or identify the differences between certain combinations of materials in adhesive bonded joints. On the left, there's a combination different than the right. And you can see obviously in the right, on the right, how the material itself, the substrate itself is deforming. And that means we have basically relatively weaker substrate, which is leading to a peeling effect that causes failure in a totally different mode than the one that you see on the left-hand side, simply because the stiffness of the joint is much higher, and therefore you can see the interfaces building strains without much deformation in the actual substrates, and therefore you see totally different failure. Again, on the right-hand side, there is a peeling effect that starts from the top to the bottom. On the left, it's a sudden failure of the actual adhesive layer. And again, that's something that is impossible to do with conventional extensometry. Another case of complex testing that is still within the tension domain. This is a tension compression cyclic test specifically designed for spring back prediction in the automotive sector. It uses a tension machine just like any other machine, but we have to couple that with a special fixture to prevent the material from buckling. So we call it anti-buckling device. And then we need to monitor or measure those strains. The difficulty here is with an anti-buckling device, as you can see in my picture on the right-hand side, the sample is technically buried. You can't see it because now we can only see the thickness or through the side of the material or the sample. And if the material is like 1 or 2 millimeters thick, that is almost all you have to monitor the material and measure the strains. And those strains are extremely important to measure. Not only just measure them, we need to measure them in situ of the test so that we can design and execute those tension and compression cycles that you see on the left-hand side. We should be able to monitor the strains during the test and then reverse the machine when we hit a particular value. And that's basically what can be done with the IC. And again, it's difficult, if not semi-impossible, to do with conventional extensometry. This is a video that shows tracking of the deformation from the thickness view of this particular sample. And you can see it basically going up and down in tension and compression. At the same time, at the bottom left, you can see how we monitor the distribution of strains. At the beginning, the material is very uniform. And so there's almost a line strain, but then ultimately, as you can see right now in the video, it's jumpy because the material is entering a banding regime, which is causing this jump in strain. The critical area of high strain rate testing, or testing at high speeds and high strain rates. It's a simple fact. If you want to simulate events like crash, impact, then you need data. And that data is simply tension testing data at different speeds. And the typical scenario is that we have so many issues associated with this type of test that typically you have a nice material behavior at low strain rates, as shown on the right-hand side, which is the blue curve. And every time you increase the speed, you get more and more trouble. And ultimately, when you enter the high strain rate regime, like 100, 200, 500, 1,000 strains per second, your curves are typically not of a high quality to give you any meaningful insight about the material response. And so this is a very critical area where DIC brings a lot of value. Now, this is, again, very complex area, and we have another webinar/demo in November about this particular topic. But for today, I just selected a couple of slides to highlight what are the issues and how can DIC be used here, or why is it used here versus conventional extensometry to produce better data. So this is just an example of a machine on the left-hand side that is used for this purpose of testing. It's nothing but a fast machine, basically. It can pull samples at 20 meters per second versus your conventional machine. At quasi-static rate, it can do maybe 20 millimeters per second. So this is maybe 1,000 times faster. And with DIC, it allows us to resolve some of those issues that are encountered in high-speed testing. One of them is the fact that when you go faster, obviously you have a shorter amount of time to measure or collect data. And when we are talking about 100 to 1,000 strains per second, you have about 1 millisecond, sometimes less, sometimes more at those speeds. And even though we have data acquisition systems that can capture data at that rate, which is for load, there isn't an easy way to capture the displacement or the strain at that kind of a rate or that kind of frequency. And of course, the second problem is you can't use any form of contact extensometry here. So everything has to be non-contact and has to be synced in a very accurate manner with the machine in order to couple the two together in order to get stress strain curves like the ones that you see on the right-hand side. So this is just an example of a video that's taken with DIC, because DIC is nothing but a camera measurement. So if you can replace a conventional camera with a high-speed camera, in essence, you can obtain strains at very high speeds. And that's basically what is shown in this particular video. Just using high-speed imagery and then using the same principles of correlation, we can obtain strain data, and we couple the strain data with the force data or stress data, and now we have a stress strain curve as the one that you see here on the screen for about 750 strains per second. Final case for tension is foils. This is a new area. I mean, it's actually not a new testing area, but there's new emphasis on this area because we see a lot of foils around us, and there are lots of materials that are being investigated for different applications, and now we have to deal with foils. Now, in principle, there's nothing really different between testing a foil and a sheet. It's the same machine, the same, to some extent, grips, and so on. The only difference is that the sample is really tiny or thin. But in some cases, it's extremely thin. And I'm showing here a picture on the left-hand side just to give you a sense of it. This particular foil on the left-hand side wasn't really a very difficult foil to deal with because it was 50 microns. So that's considered 60 microns. That's considered okay. Sometimes we have lower thicknesses. Now, regardless what, once we enter the foil domain, when you really drop below 500 microns, like half a millimeter, it's really difficult to use any clip-on extensometer because you're going to damage the sample before you start the test. So that's period out. So you have two options. Either use DIC or any other non-contact extensometer technology like laser or video. So that sounds okay. In many cases, yes, video or laser extensometers can work. And so I'm going to give you a couple of examples where either technology would work. If you have thin foils, but the strength of the foil is very strong, then it is technically not a significant problem. You can use laser extensometers and you can use video extensometers. So long you can provide those marks on the sample for the system to track it, then you should be absolutely fine. And the reason I said it's not necessarily a big problem with thin foils if the strength is high is because your likelihood of damaging the sample is lower. The same thing if your foil is sort of generous in terms of thickness. And we always say internally for us, if it's above 50 microns, it's tolerable. You can put a couple of marks, you can put like these laser extents markers, or you can paint it for DIC. But in both cases, we always say you must be very careful because you could potentially affect the sample that you're trying to test. And if things are not done properly, it will lead to premature failure in the sample. And again, I want to show this video again. And that's what we typically look for. Regardless what the strength and thickness of the material, we look for nice deformation without any significant hot spots, and ultimately, ideally, we would want to see failure in the middle of the sample. Now, in these particular two cases, this is where we have to say that conventional or laser slash video extensometry could offer an advantage over the IC. If you can actually track the material deformation without having to paint it, that is actually better than using the IC, because obviously the IC here is adding a layer of paint or 2 layers of paint, and that could affect the properties of the material and also could affect the sample itself when you handle it. But then we go to some extreme cases. When we go to high speeds, if you're doing high speed with foils, now we're going back to the same scenario as sheet metals before, it's really difficult to use conventional extensometry, and then DIC has to be used in the same fashion in a intermediate speed or high speed mode, just like we've done before, and this is just an example of it. Then we go to the extreme of the extreme. When the thickness of the foil drops below 10 microns, then it's really, really difficult to use anything. Because now your problem is not really the type of technology. The difficulty is how could you use any type of extensometer, whether it's video or laser or DIC, without damaging the sample while you're marking it. And so here we say all technologies are comparable. It only depends on your preparation of the sample. This is a 4 micron sample. Ultimately, it was done with DIC here to show that it can be done. And it can be done reliably, and you can see it's a nice stress strain curve, about 6–7% for this material. Very nice strains, but it's not straightforward to do it with any of these techniques, because the main issue is how to make sure that you don't affect the material itself during deformation. Okay, so that was the collection of examples that I have for the tension testing, and now I'm just gonna go over a couple of examples for the more complex mode of biaxial tension, just to spice it up a little bit and show that there are some cases where we could consider DIC versus conventional extensometry. And with biaxial testing, we have several types of biaxial tests. This could be a mechanical stretching test, as known in the automotive sector as Nakajima or Marciniak. It could be a hydraulic or pneumatic bulge test, which is basically a friction-free test. And there's a third type, which is more complicated, we will not cover today. It's called the cruciform biaxial testing. But at least in the first couple of types of biaxial testing, you could use non-contact extensometry, laser, video. No problem with that. It just depends on the objective of the test. And in some cases, those are adequate. In some cases, they are not. And that's where you have to use the IC, because it offers you advantages related to material deformation and failure. So this is a schematic of how a typical biaxial test is done. You typically use a machine like the one shown on the left-hand side. This is a metal forming machine or sheet metal deformation machine. In the area that is circled, that's where you change the type of tooling in order to achieve different types of tests. And in this particular case, I'm showing schematics on the right to show the Nakajima and Marciniak tests. These are typical biaxial tests that are performed on sheet metals in order to generate an FLC. And to give you a little bit more details about how it's done, with that particular setup that I showed, you change the sample geometry as shown here in order to achieve different deformation modes or biaxial ratios, as shown on in the schematic on the top right corner. You can, with the control of the sample, you can achieve tension, you can achieve plane strain, and you can achieve balance biaxial. And that depends on the sample, and ultimately you can generate an FLC as shown at the bottom right corner. But how can this test be done with and without the IC? In essence, you can do these tests without the IC. In fact, they can be done without any extensometry per the standard. The ISO standard dictates that you can do it in a post-deformation mode. However, it's not actually very accurate. And so the use of extensometry, non-contact extensometers and or DIC will help improve the accuracy and the repeatability of these tests. In very particular cases, only DIC can be used in order to provide certain type of outcome. And I will explain a couple of them, including basically the FLC generation with the new methods. So here's an example of a video done with DIC with a typical Nakajima test. Again, the nice thing about it with the use of DIC is that you can monitor the deformation of the sample. You can measure the axial ratio between the X and Y, and so you can determine whether it's balanced biaxial or not. In this case, it's almost perfect. And also you can see where the sample fractures exactly. So you can study closely the fracture of the material, if it's favorable or not. This is another example where DIC is the only option to get really meaningful output out of the test. So it's a similar test. In this case, though, we are monitoring the section distribution of strains. And you can see those sections in my video on the left-hand side. They're vertical black lines that represent virtual sections. And on the right-hand side, we can see the distribution of those sections or section strains. And that is necessary in order to generate an FLC by the ISO method. And without it, you cannot generate it by the ISO section method. There's a second method in the ISO now, which is the time-dependent approach. And the time-dependent approach, or approaches actually, there are multiple of them, rely completely on the use of any strain measurements that tag basically the amount of strain to time. And without DIC, you really cannot track and measure those effective strain accumulations up to the point of failure. And so that's where it's uniquely used to support this kind of testing. One last example, a couple of examples about the use of DIC with this kind of testing. If you are not interested in FLCs and you just want to achieve particular loading cases, in this video, we show how you can achieve true plane strain condition in a sample with the use of DIC, because you can monitor and measure everything accurately. And this is another case without a video, just images showing how if you want to achieve a pre-strain level, sometimes there are tests that require you pre-straining the material to a known value. In this case, it was 5%. And we show here a couple of examples of how this was done, where the material followed a perfect biaxial profile. As you can see, the X and Y ratios of strains are exactly the same. And then we can take the sample to about 5.5% before we retract it back with a spring back of 5% to achieve a specific amount of strain, which happens to be 5% in this case. Last example we have for today is about another type of biaxial testing, which is the friction-free testing. And that can be done with bulge testing. Whether you use a liquid or gas, in essence, it's the same technique. Just we call it hydrostatic bulge testing. And the schematic for it is shown here. You use the same kind of a machine, again, as we showed before, like a BUP machine or a metal forming machine, and you just replace the tooling from mechanical tooling to hydrostatic, basically bulging. And with DIC on top of it, we can monitor the evolution of the shape of the sample as the test progresses. And just like before, you can do this test with DIC or without DIC. You can use optical, laser, or video extensometers. But in this case, they have to be, of course, multi-axial. You have to have the ability to measure epsilon X and epsilon Y, which does exist and can be done. This is a video example of a typical hydraulic bulge test that we perform on high-strength steels. You can see in the video that we try to construct here, or we constructed on the top left, a stress strain curve for this material. And this is where DIC is unique. If you're just measuring the strains in the X and Y in the bulge test, then you can do it with conventional extensometry. If you truly want to construct the stress strain curve, then it's much easier and more accurate to use digital image correlation as shown in this video. And that's for a simple fact, because DIC, in addition to allowing us to measure the strains, which obviously we can see it on the right-hand side, we can measure the strains in 3D, it allows us to also measure the curvature of this bulge sample as it is deforming. And that is a requirement in order to calculate the stress that is shown on the top left of the video. So in order to construct the stress strain curve for the material under bulge testing, you need basically DIC. Similar test in principle. This is just for a polymeric material. shown here in a pneumatic mode instead of a hydraulic, or instead of liquid, we're just using gas. And as I said earlier, it's technically the same exact principle in terms of the testing approach. We just basically use gas to deform the material. And again, in terms of principle, you can use video or laser extensometry, but if you want to calculate stresses and strains, then you must use the IC in order to capture the curvature of the sample. One last example here is, what if you have to do bulge testing of thin foils like the ones that we showed earlier? This is a perfect example of how it can be done. Again, this is maybe an extreme of the bulge tests. This was done on a 4-micron foil, and we repeat the same exact rule. You can do it with any extensometer here, so long, whatever technique you use, so long you minimize the interference and the influence on the sample itself. You mustn't forget that the IC always requires painting. So imagine a 4-micron foil. When you apply a layer of paint, you're technically interfering with the material. So this has to be checked. And if it can be done with other extensometers without applying anything to the sample to preserve the sample, then that's fantastic. If not, in this particular case, this is a copper foil, so it's very shiny, very smooth, very nice. There are no contrasts, so applying adhesive tapes, basically markers, for a laser extensometer to follow it is really difficult, if not impossible. And so you would want to look for either video extensometers or these advanced extensometers that require no markers, and or use the IC as we've done here, but you have to be super careful about how you paint the sample in order to obtain your stress strain curve. So this was my last technical slide, and we wanted to conclude with the general note that DIC is a very, very powerful tool, no question about it. Is it the tool to go to all the time? No, not necessarily. And we try to highlight in this webinar that there are so many special cases where DIC is very powerful and or the only option to get the right results in terms of strain measurements. But in my estimate, that's just my personal estimate, this is not more than 5 to 10% of the total number of cases where you actually encounter in material testing. The vast majority of users out there are performing standard tests, whether it's tension or related. And for those cases, it might be just easier not to mess with the IC and just use conventional extensometry. In those cases that you can use either one of them, typically the IC is more time demanding or consuming, and it requires a particular skill. So that's why we always encourage people to clearly study the case, because sometimes there's no need for it, and sometimes you're just adding complication to your testing. But in those particular cases where you need it and you can benefit from it, then the IC is a fantastic and a powerful tool. Now, one last question we get asked sometimes, which is, okay, DIC is fantastic. I still believe I need it for my testing. So which DIC system is best? And obviously, we'll talk about this in a second. There are a couple of main types of DICs out there, or two types of vendors that really provide these DIC systems. And so to give an honest and clear answer to everyone, I'm going to divert away to another industry completely. So hopefully this example would demonstrate this particular question and give a nice answer to it. So I'm a particular fan of the aerospace sector, airplanes in particular, and I wanted to use this as an example here, a platform for answering this question. I put here on the screen two airplanes that are technically equivalent, the same size, the same specs, and so on, by two very popular names that should be known to everyone here. Of course, Boeing and Airbus. So the 777X and the A350 are technically the same kind of an airplane. And so the question is this, you should ask yourself this question. When you fly out there, number one, do you really pay attention to what kind of airplane you're riding or you're taking? And does this really make the airline that uses either one of the airplanes better or worse, more efficient or less efficient? And the true answer is that by all means, both airplanes are comparable, indistinguishable. And like I said, 80 to 90% of people when they fly, they don't even know the difference between this airplane or that airplane. And actually, there isn't really much of a difference. It doesn't really affect the operation, it doesn't affect the flight, it doesn't affect even the airliner in terms of whether it's this aircraft or that aircraft. They are indistinguishable. However, the success of the airline depends entirely not on the type of airplane, but rather on the use. How do they put these airplanes to use? And that's what makes your experience maybe more positive than other experiences with airliners. And that could be carried over exactly the same way to DIC systems. There are two major DIC systems out there. Which one is better? They are indistinguishable. Because DIC doesn't really depend on the actual system. If you look at the two systems and any other systems out there, they look exactly the same because technically they're just a couple of cameras and a couple of lenses, nothing more, and a software. And so in essence, these components are exactly the same. You could potentially use the same camera and the same lens and the same lighting in either case. And so specifying the right DIC system obviously is important, just like specifying the right aircraft for your basically use as an airliner. You don't want to buy a very large airplane for an application or a route that requires a small airliner. And the same thing here. When you pick your DIC, it's very important that you pick the right cameras, the right lenses. And in our opinion, beyond that, there's not really much to it, because lighting is very very similar. Only special cases require special lighting. And as for DIC softwares out there, even your own algorithm that you develop by MATLAB will get you the same result. So after you spec your DIC system, what's more important to remember is that it's how you put this DIC to use. Developing the right skills for using DIC is really what's going to get you the outcome. And so this is why we always give our advice, which is before you get a DIC, please ask people who use DIC. Ask your colleagues, a bunch of people in academia use DIC today. So ask them about their particular cases of use, because sometimes we get or we hear the general label, DIC is fantastic, it can be used for everything. And truly, that's not correct. Sometimes it is, yes, powerful and can be used in many cases, but sometimes it's an overkill. So ask people around, and then once you decide to go in this direction, then definitely after you spec the right system, you have to put some investment into developing the right skills, because ultimately it's an art, and you want to get good results, you have to invest and develop those skills. So this was my last slide. I wanted to thank you all for your attention today. I hope this was useful to you, whether you use DIC or not, or you're thinking about it. Before I conclude and hand it back to ASM, I just wanted to spend 10 seconds to talk about other webinars that we have planned in the future and in the near future. On the left-hand side, this is a fantastic opportunity for those people who are interested in any sort of material testing. Honestly, metals, composites, plastics, polymers, different conditions, different types of tests. We have this virtual testing forum that is organized by Zwickholm. This is typically done in-house in Germany. However, of course, obviously this year, because of travel restrictions, it is done virtually. So this is the first year for it. But this virtual testing forum will cover several topics, and there is already a nice schedule for multiple presentations and demos that are available. If you go to the link that I'm highlighting in green at the bottom left corner, you can see those particular presentations and demos and webinars, and you can register for as many as you want. They're all available, and most of them, if not all of them, are available at 2 time slots, basically to offer the same experience for people across the globe, whether you're east or west. I'm just basically highlighting on the right a couple of particular webinars. The first one on the top right is for general mechanical characterization. This should be a nice explanation and overview of multiple testing scenarios with material testing systems. And at the bottom right, this is the webinar I indicated earlier. We will be doing a demo and a webinar in November about the topic of high-speed testing. Again, thank you so much for your attention, and I will hand it back to Joanne from ASM for the questions and answers. Thank you.
Thank you, FADI, for that excellent presentation. We are really out of time, but I want to ask one question, and then the rest will be sent to you to answer post-webinar via email. An attendee wants to know, is the stress strain data obtained from the DIC or from the Zwick-Rowell tester?
This is basically, if I showed it with DIC, then it's obtained from DIC. So basically, we obtain the force from the load cell on the material testing system, and we convert that to stress, and we obtain the strain from the DIC, and we merge them together to generate such a stress strain curve. So basically, it's a combination from the two systems.
Combination. Okay, thank you. Unfortunately, we don't have time to answer all of the questions we received, but in a few days, all participants will receive an email with further contact information. I also encourage you to complete the brief survey that will appear on your screen as you exit the webinar. With your input, we can continue to provide webinars with high-quality practical information. I also encourage you to follow up with FADI for more information about digital image correlation in support of complex testing of advanced materials. Once again, I'd like to acknowledge the sponsor of today's webinar, Zwick-Rowell. For more than 160 years, Zwick-Rowell has stood for reliable test results, excellent service, and quality and reliability in materials and components testing. For more information, visit www.zwickrowell.com. And thank you again for participating in this ASM webinar. Have a great day, everybody.